So I'm Ahmed Rian, sales engineer in charge of the East Coast of the US and Canada at Gentec-EO. So happy to be here. Now, did you know that it was a pulse laser that was first developed before the continuous laser in 1960? It took one more year for the CW laser to appear. So guess who made the first commercial energy meter on the market? You guessed it right. It was Gentec-EO. Here is the first page of the spec sheet almost 50 years ago. Colors of the company has changed at that time, which is not a bad thing in my opinion. So, at Gentec-EO, we have been providing laser beam measurement instruments since the 70s. Our core values are partnership, accuracy, and rigor. We work with our customers to achieve the most accurate measurement solutions, standard or custom, to get your business focused on what is valuable. Among other product line as beam profiler and power meter, at Gentec-EO, we design and manufacture a wide range of professional grade, high accuracy laser energy meters. So anywhere there is a laser, there is also the need to measure its performance, right? Whether it's R&D, manufacturing, or medical system, lasers, and especially pulsed laser, plays a key role. So let's get into more details about the application where we need pulsed lasers in the next slide here. So there are countless applications where you need to use a pulsed laser as in the telecom products, for example, medical application as dermatology or ophthalmology, and laser source development as well. So those pulsed lasers start from less than few millijoule to the kilojoule energy per pulse. Now, does the laser system in those industries and applications always produce the exact same energy per pulse? One may be tempted to assume that the laser always produces energy as per their specifications and that it will never change over time, but the reality is often very different. In fact, we will see the reason behind this performance degradation later on. Now, a trend we've noticed in the need to make measurement processes run faster and more efficiently. People are using lasers with shorter pulses and higher repetition rate. It is also getting more and more important to monitor each pulse's energy. A few years ago, most people who use pulsed lasers were fine in simply checking the average power of the pulsed laser. Average power is still a good indicator of the good health, let's say, of their system. But we see more and more cases where each pulse and variation in energy from one pulse to the other can be very critical. So to measure the pulse per pulse energy, you need, of course, an energy meter. I divided this presentation in 5 sections, as you can see here. So let's start with what is a laser energy versus laser average power. It may be obvious for most of you. Allow me to quickly remind the difference between CW and pulsed energy. First, let's look at CW laser. Its power output is constant, as you know. You can calculate the energy it has delivered during a certain period by measuring the area under this curve. Now, let's look at pulsed laser with the same average power. The energy is accumulated during a certain period and only exits the laser during a very short duration. The area under the curve is the same because the total energy in each period is the same, but the peak power is much higher than the average power. It is this concentration of power that we use in pulsed laser system. Quick example here, if we have, for example, a laser with 100 millijoule energy per pulse and 10 pulses per second, we would have then 100 millijoule multiplied by 10 hertz equal 1 watt. That would be the average power of your pulsed laser. Now, laser manufacturers will often give you the peak power, which is the energy per pulse divided by the pulse duration, which is, let's say, in our example, 100 nanoseconds. So we would have 100 millijoule divided by 100 nanoseconds equal 1 million watts. So peak power may be very useful to know for application, but when choosing the right energy detector, the energy density is what we need to know. how much energy you are shooting on a certain surface at each pulse. So pulse laser effect will be much more localized and targeted than the CW lasers. The heat transfer will be more limited and the work more precise. Now, why should you measure energy? Many factors can impact a laser system's output and stability of your energy per pulse readings. For example, the optical components and the surrounding environment have an impact on the energy your beam delivers. The intrinsic noise of the pulsed laser is also an important factor since it has a large impact on the pulse-to-pulse energy stability. Over time, those elements will inevitably affect the performance of your laser and consequently the quality of the work to be done with it. Therefore, at the end of the day, measuring laser energy will save you costs. There are three main, let's say, contexts where someone needs to measure his laser energy. Novel pulsed lasers are often developed in academic or research environments. Accuracy and repeatability add credibility to your research. So pulsed lasers are typically required to develop new processes, and it's good to be able to characterize both the laser system and the process precisely. It could be also in the system design and production context, where you need to monitor the behavior of your laser to make sure it is performing as expected. So very important to remember when you are in this design stage, you have to keep in mind the design validation of your system, right? You could develop a control loop, for example, to gather continuously some important info about your system. Another aspect that is important, especially in the medical application, is the safety certification, which is mandatory to comply with using an accurate, precise, and least traceable energy detectors. You could also need to do alignment at different places of your system for assembly. Finally, you have to think in a context of diagnostics for repair maintenance purposes, where the places in your system you need to measure the energy, power profile, are these points accessible. It could also be in the field service context, where you need an energy meter for diagnostics purposes and do troubleshooting when your laser is not working properly. In this case, a portable solution is preferred as it's easy to carry around from a laser to another by the designated technician. Now, let's discuss where exactly you need to use an energy meter in your setup. So by adding an energy meter, you can monitor your system performance. Sometimes you need to measure the energy for diagnostics purposes. In that case, you should gather that info in different points along the light path. Note the detector in this case, in this example here, is offset. We move the energy meter away from the focal point. This is done to avoid damaging the surface of the detector. Very important to know that it will still produce an accurate measurement as long as the beam is still fully captured. Now, you can choose whether to do direct or indirect energy measurement. This choice will dictate the energy meter technology. Direct laser energy measurement at a given time delivery point, you will measure 100% of the laser energy. In this case, you will have to watch out for damage thresholds. The direct measurement can be used in the pulse or pulse energy mode or in single shot energy measurement mode. We will discuss in more details about those measurement modes later on. Indirect measurement, you will measure a pickoff, a portion of the beam from a splitter or reflection. This is done in real-time monitoring, and it involves often smaller detectors. Speaking of pickoff, you can use for the indirect measurement a beam splitter as our PA series. You are even able to do inline beam profiling while measuring a portion of the beam energy. This is often used for relative energy measurements. Here we can scale up the same logic of multiple measurement checkpoints in a huge scale. Here we see some examples of lasers that go in the terawatt to petawatt range. For those who just remembered, the power I refer to is the peak power and not the average power. Right? We can curb the pulse energy to hundreds or thousands of joules at the end. But to achieve this, we need to monitor the energy level at every step to know where the amplification process can be improved. So first, it must be measured at the seed laser level. At this point, it is telecom energy level. Low energy, small detectors with high resolution, right? It's then pumped and pumped again. And each step, this must be measured, as we need to ensure that the energy level you have reached before you get into the next application stage. Each step requires a different type of detector because the beam parameters are very different from one amplification level to the other. Usually all these detectors are connected through Ethernet since the whole laser system can take a full role. Now, let's talk about what are the best tools to measure the energy per pulse of your laser. Generally, we would ask to provide us those following laser specs: the wavelength of the laser, the minimum maximum expected energy per pulse or average power, the expected beam size and profile, the repetition rate, the pulse width and type, and detector communication interface. We have different options as standalone monitor through DB15 connector, the USB to your computer, Ethernet, etc. A lot of communication interface are available. So depending on your setup, these parameters may actually be different from what the laser manufacturers provide. Beam size and power are affected by optical components used in your setup, by aging parts, or by specific elements to your measurement environment, such as temperature or air circulation. Let's spend a little time on the most important parameters to take into account when choosing an energy meter. So the first thing to consider is the energy range you need to measure. To cover the lower end of the range, you will need to make sure the detector you choose has an NEE, which is noise equivalent energy, 20 or 30 times below the minimum energy you want to measure. For example, if you need to measure 100 microjoule, you will need to select the detector with an NEE of 5 microjoule. On the high energy end of your range, you will have to consider two parameters. The first one is the maximum specified energy, and the second one is the maximum energy density at the wavelength and pulse width you are working at. Second thing to take into account is the laser beam diameter. In general, you need to select a detector whose active area is about twice that of your laser. This helps to ensure that the entire laser radiation is absorbed by the detector. It also helps averaging out any spatial non-uniformity that could affect the measurement and make it easy to align the laser beam properly. Also, you always want to center the laser beam on the sensor, since this is the way both the laser beam and the sensor are aligned during calibration. This method will give you the most accurate and repeatable measurement. Now, the pulse width and repetition rate, another very important parameter to take into account for the pulse lasers. So before selecting a detector for your pulse energy measurement, you need to be sure that the pulse width of your laser is shorter than the specified maximum pulse width of the detector. This is to ensure that the voltage output is linear and directly proportional to the laser pulse energy. In addition, make sure that the laser repetition rate is less than or equal to the specified maximum repetition rate of the detector as well. So now maximum energy density, it determines the point above which the absorber material of the detector can be damaged. So our typical maximum energy density specification can vary dramatically depending on the type of the absorber material. It can be as low as 50 millijoule per centimeter square for our BL absorber, or as high as 600 millijoule by centimeter square for our MB absorber. These values are good for 7 nanoseconds pulse at 1064 nanometer. Beware, however, that the maximum energy density decreases as the pulse width gets shorter. Last point to take into account is the maximum average power. Now, someone could ask why the average power is concerned when selecting an energy detector. It's important to keep the average power below the maximum average power of the detector because it relates to the accuracy of the measurements. Like all detectors, pyroelectric detectors, for example, have a temperature coefficient, which is about 0.2% per centigrade temperature variation, affect the voltage responsitivity of the detector when in operation. For example, a 10 centigrade temperature increase due to high average power would result in plus 2% change in the responsivity. Staying below the maximum average power specification ensures you that your measurements are within our uncertainty specification. Now, to help you choosing the right detector, we developed an amazing tool on our website called Product Finder. It will help you pre-qualify the best detector for your application based on your laser specs. It will even give you a list of detectors that match the best your requirement based on the input parameter, as you can see in this example here. You can also reach us directly. We offer guidance on a daily basis on the best practices in laser energy measurement for you to get the most of your lasers. Now, let's jump to different energy detectors that we have to offer. Here is an overview of the energy detector technologies in terms of maximum measurable energy. I'm using log scales here because the energy ranges are very wide. One thing to notice from this graph is that generally speaking, the technologies that can measure higher energies tend to be slower. Let's have a look at each of these technologies. I'll start with pyros because this is the most widely used technology to measure energy. The way pyroelectric energy detector works is it absorbs the laser pulse, diffuses its heat, and the change in temperature generates a signal. We can then use some electronics to amplify and convert that signal into a measurement. Pyroelectric sensors are a very popular choice because they are very versatile. They can measure from microjoules to hundreds of joules. They are spectrally flat, so pretty much any wavelength can be used, and their damage threshold makes them resistant to small beams. Compared to photodetectors, the trade-off is their slower rise time. Generally speaking, large detectors can measure higher energy, and smaller ones are faster. As I mentioned earlier, people need to measure energy at high repetition rates, and we wanted to provide them solutions that requires less compromise. So we worked on improving the rise time of our fastest pyro detectors. The QE series with the MB absorber could previously go only up to 300 Hertz. Now the new models can now reach 1 kilohertz. The models with the MT absorber already has fast rise times, so they could already detect all pulses at up to 6 kilohertz. The improved version goes up to 10 kilohertz. But now 10 kilohertz was too fast for the standard electronics. So we also released a new PC interface model, the U-Link that you can see here, that's both economical and able to handle energy detector data for pulses at up to 10 kilohertz. As mentioned earlier, we have different absorber types for different applications. We know that the surface of the detector will absorb the energy and will transfer the heat to the crystal behind it. If the material is thin, it will transmit almost immediately. The downside is the risk is that the absorber won't be able to transfer the heat to the crystal behind it and will be vaporized. With the broadband absorber, it will transfer the heat slowly and the surface won't be damaged. This is in mind that the average power remains under 90 watts. Also, we need to manage the heat because the pyroelectric crystal output is temperature dependent. So therefore, the pyro must be installed in a controlled temperature environment. Now, when you have a high energy density, you should think expanding the beam to reduce the amount of energy per pulse for a given surface. Sometimes this is not possible to do because your setup doesn't allow it, or even when expanding the beam, you still have a too high energy density that may damage the surface of the detector. In that case, we suggest to use our QED diffusers that not only will expand the beam, but also will transmit less energy to the detector surface. However, it's important to take into account that there is around 50% of back reflections with this QD diffuser. One other thing about the diffuser and volume absorbers from all manufacturers is that we calibrate them as at a normal angle, like you see above. The diffuser does not behave the same in the UV range. This is why you can order it with the absorber installed and calibrate it with the detector, or you can order it without and calculate your own attenuation factor. We'll see an example of using QED diffuser in the video a little bit later. On the lower end of the energy levels, we have the photodetectors. So they are very fast and very sensitive, but they are very limited in maximum energy and in wavelength range. The maximum repetition rate with those detectors is 1 kilohertz. We also have the integrating spheres, which can be extremely fast, but also expensive since they require highly performant electronics. The energy range for those detectors is between pico and millijoules. Now, for the repetition rate above 10 kilohertz, we have a unique solution, the MACH. It can take an average power from the milliwatts to 25 watts and has an energy range from nanojoule to millijoule. It depends on the probe model that you choose. It includes wavelength correction and temperature compensation features. It can capture and store up to 4 million pulses. It can also track missing pulses and pulses lower than the user's set energy threshold. To demonstrate how fast the MACH system measures and stores pulsed energy data, we're going to see a video here. So we are going to drop an ND filter through the pulsed laser beam while capturing pulses at 100 kilohertz. We set up the MACH to collect a batch of 3,000 pulses. Now, you can see the leading edge of the filter holder occludes the beam and results in missing pulses. Then the transmitted ND glasses passes through and you measure the attenuated laser, followed by the trailing edge of the holder, which occludes the beam again. This all happens in less than 30 milliseconds. You will not have captured this with your typical energy, only with a MACH. Another example where the MACH is very useful is when you need to measure the energy per pulse inside a burst mode. This is very challenging to do without a fast energy meter as the MACH. Now, let's talk high energies. In the kilojoule range, single pulses can be measured with thermopiles or calorimeters, but you have to wait a long time between each measurement because these detectors are slow compared to the other technologies. As you can see here, for example, the time it takes from detectors to get from the baseline to peak is relatively slow. We're talking 3 seconds here. Therefore, this technology is good for single shot energy. The single shot energy mode is available with all our thermal power detectors. Allows you to measure the energy for single pulses or pulse train, ideal for low repetition rates or to measure the energy contained in a burst. It can measure single shot energy up to 500 joules. Based on the same thermopile technology, we also have a portable energy meter that is useful to measure IPL sources. The Proto 500 IPL is capable to measure up to 350 joules. This is basically thermopile in SSE mode with the integrated display. We also have calorimeters that has a large energy range from 50 millijoule to 16 kilojoule. Thanks to its slow heat transmission, it works for pulse duration from femtoseconds to 15 seconds. We have also optical aperture from 10 millimeters to 430 millimeters. The 4 calos that you see in this slide are among the custom detectors that we designed and built over the years. As mentioned in the beginning of my presentation, one of our expertise is the development of custom products to respond to our customer specific needs and requirements. We always find a way to work with you designing the right detector, even with the craziest specs. Last section here, how to measure the energy accurately. So once you made sure that the detector that you have in hand is the best choice for your laser specification, as we saw earlier, you can start by visually aligning your detector to the optical axis of your source. This is done with your laser off or the beam blocked. You can now power up or unblock your laser and use the spike test target to make sure the energy density is below the damage threshold of the detector. Now you have to make sure the trigger level is low enough to trigger on the pulses, but high enough so it does not trigger on the background noise. The default trigger level in our monitors is 2%. Now you have to set the wavelength of your laser in the monitor or PC Gentec software. So you have finally to allow a little time for the detector to reach thermal equilibrium. It's 5 to 10 minutes, for example, for the pyroelectric. You are now ready to make accurate pulse energy measurement with your energy detector. So some tips to have an accurate energy measurement. We recommend to use a target, as mentioned before. We provide it by default with our energy detectors. You have to maintain a stable environment. You have to increase the averaging and fix the measurement range. Here is now a demo where we demonstrate how to use an energy meter with our Maestro display along with our QED diffuser. So just before clicking on play, because of the slow rep rate of the laser we used in this demo in our lab, the camera doesn't capture all the pulses at the same moment. So that's why we will see some change in the brightness. Let's click on play. You will see also the laser is not very stable in the measurement, but it's around 1 millijoule. So you may have a lot more stable laser in your lab in your application. So now we will install the QED diffuser as I introduced earlier in front of the detector. We have already an attenuation factor that comes with the QED detector. So you see here without the attenuation factor, we have lower energy measurement. So now we can, through the Maestro display, enter this attenuation factor that we already have. And we will get back to the original measurement. We went, of course, through all the steps that I described before to make sure I have the most accurate reading possible, as making sure the laser is well centered on the detector surface. I entered also previously the right wavelength on the monitor display. Now, I would like to present another application where you can use the energy detector in addition to the pulse per pulse energy measurement. It's the beam profiling, where you capture the reflection of your beam on the surface of the detector and place a camera toward the reflection to capture the profile of your beam. Know that a camera can be synchronized with a pulse laser and that you can get related measurement of energy profile density, which is cost effective. Now, I already came to the end of my presentation. 4 messages I would like to reiterate are: the laser specs change over time. You may need to measure the energy per pulse periodically to make sure its performance is as expected. Second, think in advance when you design a laser system to make sure you avoid disassembling your setup to take a measurement within. And choosing the right technology for energy detector will depend on your laser specs and your application needs. And that's why we developed the product finder tool that helps you choosing the right energy meter. In the chat box, we included already some very useful links where you can go to the download center with the different application notes, specification sheet, and to our blog page where you have valuable information about how to measure accurately your energy force profiles. And below, if any question, you can use, as we said earlier, the Q&A box below. You can also reach me directly through my email or my phone number that you see in this page. Thank you very much for your time, and I'm ready for any question if there are. And thank you again.
Thank you, Ahmed. So we have already a few questions that came up. The first one is about measuring outside of the focal point. So is there any difference between the energy measurement at the focal point and at any other point outside of the focus?
Thank you, Gabriel. So there should be no difference between the measurement at the focal point and before, after the focal point. Only the energy density is changing because the beam is smaller at the focal point. So how much energy you have on a given surface. So the density will change, but the total energy will not change. So on top of that, the measurement will be the same whether you are at the focal point or not. It's important to take into account the density, the energy density of the detector to avoid damaging it. And that's why we reiterate, we repeat the message that you have to take into account that element to make sure you place the energy detector at the right position. But there is no difference in the energy measurement whether you are a focal point or after or before that point.
Thank you. I think maybe we could mention also that if you're using an extra lens to widen your beam to avoid some damage, then there might be some attenuation from the lens or from reflections. So that might also be something to consider if you're expanding your beam. Good. There was, well, actually, also on the focal spot side, there was a question about what's the best and easiest way to increase your spot size. If you have a laser that is a few microns size, so you want to make it bigger to a few millimeters. What would you suggest in that case?
So the best way to increase the beam size is by simply measuring it at another plane than the focal plane. So you would place the detector at another position along the beam path where the beam is larger, like before the converging lenses. For example, some of our customers using laser welders will remove the integrating lens when doing measurement, or they keep it, but instead lower the working surface at a much lower or higher position than normal, so that the beam is larger there. Another good way is by using a convex lens along the beam path. I think this is a good way to address this problem, which will increase the beam size. There are also beam expanders out there, which are specially made to expand beams quite simply. So we recommend always to characterize the power energy measurement. You can determine what will be the correction factor to apply to your measurement at a low energy level, and you measure it with and without the lenses. So from the difference measured, you will be able to input a correction factor as we did for the QED diffuser, but in that case, this is this correction factor is for the lens that you added, for your personal, let's say, lens that you add in your system. So you would add this in the display as the Maestro that we saw earlier, or the interface, the PC interface, PC Gentec. It allows you to add that attenuation.
Great, thanks. And we have one last one. So is it possible to measure average power with an energy detector?
So the energy detector will measure energy per pulse directly, but may calculate average power indirectly. Average power appears in statistics display of the meter to which the energy detector is connected if the meter supports this. This average power is not as accurate as the one you would get from a detected, let's say, power meter, power detector, because it is indirectly calculating using average energy per pulse and repetition rate. So let's say if you have 10 millijoule per pulse, and you have, let's say, 100 pulses, you multiply 100 pulses by 10 millijoule, and you will get 1 watt. This would be the average power, indirectly calculated with the energy meter. So still is a great way to get both measurements at the same time, energy and power with the same detector.
Great. Well, that was it. We don't have any more questions. So we still have time if there are some extra ones that can be asked. But while we wait for just a minute, Ahmed, do you have maybe a wrap up, some comments that you would like to make sure people remember?
So as I mentioned earlier, a lot of detectors, models, a lot of choice of technology. It really depends on the needs, on the requirements of the project, and we am available always to respond to those questions. Sometimes it's little details that change the need and the detector model. So that's why we take the time to go over all the laser specs, and not only the laser specs, but how you use your laser. Because sometimes the specification of the lasers is one thing, and how you use this laser is another thing. So, for example, laser can go up to, 10 joules, but you only use it at, 50% or 25%. So you won't need a detector that go up to those this high level of energy. That will allow you to go more precise, maybe in the lower the lower energy levels. So of course there is a trade-off between, you cannot have a dynamic range that will calculate from the microjoule up to the kilojoule. So there is always a bracket, let's say, of energy that you will measure, and we work with you to determine which is the best detector.
Thank you.
Thank you.
And thank you to Gabrielle and Ahmed for a fantastic presentation, for you guys to make sure you make note of the resources that Gabrielle sent in the chat box, as well as the email address that Ahmed has up on the screen. In case there's any follow-up questions, this is the best way to get in touch with them after the fact. Just another quick reminder, this webinar is recorded, so we will be posting it online by the end of the week. So you'll have access to be able to rewatch the recording, share it with your colleagues, and be able to, again, watch this content on demand later. But that's everything that we have. Thank you guys so much for sponsoring the webinar, and I will see you all at the next one.
Thank you.